Alright, so here we're tasked to evaluate some expressions involving inverse trigonometric functions, involving inverse sine in particular, and also compositions of inverse trigonometric functions and trigonometric functions. Let's just begin by a quick recall of some of the properties of inverse sine as we'll use it in all these examples. Recall that the inverse sine is a function whose domain is -1 to 1, including -1 and 1. Its range is negative pi halves to positive pi halves, including negative pi halves and positive pi halves. And the operation that inverse sine performs is we give it an input, and that input is some y-coordinate of a terminal point corresponding to a real number between negative pi halves and positive pi halves. And it outputs for us whatever that real number is. So when we're looking at this first example here, we're looking at the inverse sine of -√2/2. So this is a y-coordinate of some terminal point which corresponds to a number between negative pi halves and positive pi halves. And we need to find whatever that number is between negative pi halves and positive pi halves. Now you might recall that the sine of negative pi force is equal to -√2/2. Note that this is telling us that the real number negative pi force corresponds to a terminal point whose y-coordinate is -√2/2. For this reason, we can say that the inverse sine of -√2/2 is negative pi force. And we find our solution. Awesome. Let's go ahead and look at part B now. So for the next of these problems, you'll see that we'll work with compositions of arcsine and sine. Now we could define theorems for when these functions cancel one another and when they don't. So it turns out, although we might expect, for example, the inverse sine of the sine of 2 pi thirds to equal 2 pi thirds, because inverse functions are, exactly inverse operations of one another, we can't quite say this is true. And this is for the reason that sine is not a one-to-one function, but the inverse sine is a one-to-one function. Recall again that that's just was defined by the restricted domain of sine, or a sine function with restricted domain. In any case, we go ahead and jump into this. So my suggestion when working with compositions of trig functions and inverse trig functions is just to evaluate the inner of the composition first and then the outer of that composition to find the value of that composition of trig functions, just for the reason that we don't need to memorize more formulas. So here, let's begin. The sine of 2 pi thirds, we need to find the real, this is a real number 2 pi thirds. We need to look at the terminal point corresponding to 2 pi thirds. So we know that terminal point corresponding to 2 pi thirds would be -1/2, √3/2, and the y-coordinate there would be positive √3/2. So we're looking at the inverse sine of √3/2. And now to evaluate the inverse sine of √3/2, again, recall we're trying to find the real number between negative pi halves and positive pi halves who corresponds to a terminal point with the y-coordinate √3/2. And you might recall another terminal point on our unit circle, the point 1/2, √3/2, which corresponds to the real number pi thirds. So for this reason, we can say that the inverse sine of -√3/2 is equal to pi thirds. And we find the evaluation of the inverse sine of the sine of 2 pi thirds to be equal to pi thirds. Let's look at part C now. Part C, we have the inverse sine of the sine of pi thirds. So again, let's just evaluate the inner of the composition and then that result into the outer of the composition. So to evaluate the inverse sine of sine pi thirds, we first look at the sine of pi thirds, which we know is equal to the y-coordinate of the terminal point corresponding to the real number pi thirds, which is √3/2. The inverse sine of √3/2, note that this will be the same value we found here. The real number pi thirds corresponds to a terminal point with the y-coordinate of √3/2, and pi thirds is a real number between negative pi halves and positive pi halves. So we have our solution here, also pi thirds. So again, note that in the first of these compositions, the input of that composition did not equal the output of that composition. But in this case, the input did equal the output of the composition. And we'll see that this is exactly true depending on the input that we're given. When we see compositions of the inverse sine and the sine of the inverse sine and the sine, we'll find that this composition equals x for all x which are on the interval negative pi halves to positive pi halves, including negative pi halves and positive pi halves. And the reason for that is the inverse sine outputs for us real numbers between negative pi halves and positive pi halves. And so again, if we have, in this case we'll see this to be true in every case. And we'll see then for the inverse sine of the sine of x is not equal to x for all x which are outside of this interval. So we'll say x belonging to real numbers take away negative pi halves to positive pi halves. How about we move on to D then? So we look at the sine of the inverse sine of 1/2. So when we look at this composition, we start by evaluating our inner of the compositions, the inverse sine of 1/2. And we can think to ourselves, well, on the unit circle, what real number between negative pi halves and positive pi halves has a terminal point with the y-coordinate 1/2? And we could think to ourselves, well, hey, if we look at this real number, pi sixths, its terminal point is √3/2, comma 1/2. And this is a terminal point with the y-coordinate 1/2. So here we can say that the inverse sine of 1/2 is equal to pi sixths. So we have the sine of pi sixths. And the sine of pi sixths, c is just 1/2. And we can evaluate this expression. It's equal to 1/2. Now, it turns out that this composition will always have this, definition of inverse property or inverse functions met, where we can say in every case the sine of the inverse sine of x equals x for all real numbers x. Or excuse me, not for all real numbers, but for all real numbers which are in the domain of inverse sine, so all real numbers between -1 and 1. So here's those three theorems that you could memorize if you wanted to, but you're not, again, I suggest just evaluating compositions of inverse trig functions and trig functions a step at a time. Let's go ahead and move on to look at part E. So part E, we look at the inverse sine of 2 pi thirds. So to evaluate the inverse sine of 2 pi thirds, we try to find a real number which, real number which corresponds to a terminal point whose y-coordinate is 2 pi thirds. So this is a trick question for maybe two reasons. Well, again, recall that the domain of inverse sine are y-coordinates of terminal points. So here we have some 2 pi thirds. This looks more like a real number. That's an increment of pi sixth or pi fourths, in this case pi sixths. This looks like a real number that corresponds to some terminal point. It doesn't look like the y-coordinate of a terminal point. For this reason, this problem is a trick question. Now, why else is this maybe a trick question or not a trick question? Well, consider this value does not exist. Why doesn't this value exist? Note that 2 pi thirds, pi is about 3.14, right? So this is like about the value 2 times 3.14 divided by 3, which is definitely greater than 2. Or it's definitely greater than 2, it's definitely greater than 1 as well. Well, what's true about numbers greater than 1? Well, they're outside the domain of inverse sine. So note that 2 pi thirds does not belong to the domain of inverse sine, which is numbers between -1 and 1. Again, we have our epsilon for belong to crossed out to say does not belong to. And therefore, again, this is the domain of the inverse sine. And so therefore this expression does not exist because 2 pi thirds is outside the domain of inverse sine. Let's go ahead and look at the inverse sine of the tangent of pi force. So to evaluate this, we start with the tangent of pi force. We know tangent of pi force is defined as the ratio of the y-coordinate and x-coordinate of the terminal point corresponding to the real number pi force. That terminal point is root 2 over 2, comma root 2 over 2. The ratio of those coordinates is 1. So we're looking for the inverse sine of 1. What is the inverse sine of 1? Well, the inverse sine of 1 is the real number which corresponds to a terminal point with the y-coordinate of 1. And we don't know the only point which that would be true for is the point pi halves, at least for values inside the range of inverse sine. The only real number would be pi halves. And so we have our solutions here.